Hi, I'm François. I'm a software engineer on the Keras team. In this session, we'll talk about data preprocessing for machine learning, what it is, what the challenges are, and how the Keras API can make it easier for you. There are two big use cases for data preprocessing. The first one is what's called data vectorization. If your input data contains text or categorical values, you cannot feed it directly into a neural network. Neural networks can only process numerical values. And further, it's usually a good idea to normalize or rescale numerical inputs to restrict them to small values, typically in the 0 to 1 range. The second use case is data augmentation. Data augmentation is mainly used when processing images. The idea is to generate random variations of an incoming image on the fly so as to expose your model to a greater diversity of inputs during training. It's a great way to make the most out of a small dataset and train models that generalize better to new images. A key challenge with data preprocessing is what's known as the training savings queue. Machine learning models can only make sense of inputs that stay very close to what they've seen before. For this reason, it's very important that the preprocessing setup that you're using when you deploy your model in production stay very close to the preprocessing setup you used when you originally train your model. For instance, if you deploy a text classification model in a mobile app, you're going to need to make sure to recreate in your mobile app the same text encoding system used at training time. This can potentially get very challenging. Any small discrepancy can have a large impact on real-world performance. And this is something that we've repeatedly observed with production ML systems at Google. This is a very difficult and very important challenge. We designed the Keras Preprocessing Layers API specifically to address this challenge. Keras preprocessing layers are modular building blocks that encapsulate common preprocessing steps, such as vectorizing text, rescaling image values, hashing categorical features, and so on. A key feature of this API is that it enables you to place preprocessing computation either in your data pipeline or directly into your model. This means that you can create end-to-end models that are capable of processing raw inputs, such as text or structured data dictionaries, and these models can be deployed as is. That way, you don't have to re-implement your preprocessing logic when you deploy in a new environment. Because the preprocessing logic is part of the model itself, you're guaranteed that you're using the same logic in production as what you used during training. We'll dive deeper into this feature in a couple of slides. To make things concrete, let's look at a practical example. We're going to do text preprocessing for a sentiment classification model. In this example, we look at text files on disk. Each text file contains a movie review from the Internet Movie Database. We have two folders. One folder with reviews that had a high star rating associated with them, positive reviews, and one folder with reviews that had a low star rating, negative reviews. Here are the steps of our workflow. We start with text files. We set up a TF data pipeline to read the files on disk and turn them into a dataset object that outputs string tensors. Then we use Keras preprocessing layers to turn these string tensors into numerical values. Finally, we're able to feed these numerical values into a Keras model for classification. The first step is super easy. We can do it in one line with the utility image dataset from directory. It will look at the subfolders of our reviews directory. It will list the text files in these folders, and it will interpret each subfolder as containing examples for one category in a classification problem. It will then create a TF data dataset object that outputs text strings and their corresponding labels. Here we have two subfolders, positive and negative, so we'll get a binary classification dataset. Next, we need to encode the text strings into something that can be processed by a neural network. This involves several steps. First, we need to standardize each string by converting the text to lowercase and removing the punctuation. Next, we need to split the string into individual words, which is called tokenization. Then we need to build a vocabulary that maps unique words to indices in a dictionary. Once we have that vocabulary, we can look up the words that compose each string and convert the string into a sequence of integer indices. Finally, we'll turn our indices into numerical vectors. There are multiple ways to do this, but one of the simplest ways is to apply multi-hot encoding to the indices to turn each string into a single binary vector. Keras makes this entire process easy via the text vectorization layer. It offers a range of common options for text encoding, including different ways to customize the standardization step and the tokenization step, and different ways to turn indices into vectors. In this case, we'll consider the top 10,000 most common words in the dataset. We'll standardize by converting the text to lowercase and stripping the punctuation, and we'll split the text on a white space. Finally, we'll encode the indices via multi-hot encoding. Before we can start using the layer, we have to learn a vocabulary, and we do so by using the adapt method. Here we call adapt with a dataset that outputs the text samples of the training data and which discards the labels. As you can see, once the layer has learned the vocabulary, it's capable of turning a string into a binary vector that encodes what words were present in the string. Here's an important issue when preprocessing data, in particular text data. You could do it sequentially by preprocessing one batch of data on CPU and then feeding it to your model that runs on GPU. But then your GPU will end up being idle a lot of the time. It will be waiting for the preprocessing stage to be done with the data batch before it can start looking at it. The solution is to do preprocessing and training in parallel, asynchronously. TensorFlow has a great API to do this in TF-Data. You can map preprocessing computation into your TF-Data dataset to be handled asynchronously on CPU while your GPU is processing the previous batch. Let's take a look. You can simply take your labeled dataset and map your vectorization layer into it while specifying how many threads of parallel computation you want to use for the CPU preprocessing. If you were to do it in pure Python without TensorFlow, it would be quite challenging, but TensorFlow solves the problem in a single line of code. At this point, we have a dataset that outputs preprocessed text samples and their labels. I said earlier that preprocessing layers enable you to place your preprocessing either in the data pipeline, which is great during training, or in the model itself, which is great for inference, since it bypasses the problem of the training serving skew. And here's how it works. For training, we construct a model that expects preprocessed inputs, and for inference, we construct a model that expects raw string inputs. This model includes the text vectorization layer as the first layer in the model. Finally, we can train the model, and once it's trained, we can use our end-to-end model for inference and raw strings. And that's the end of our talk. And remember, the key feature of Keras preprocessing layers is their versatility. You can use them in a data pipeline to do asynchronous parallel preprocessing during training, and you can also use them directly as part of the model to create end-to-end models that package their own preprocessing. And that's great for inference, since it enables you to bypass the training serving skew problem. To learn more about what you can do with Keras preprocessing layers, check out our guide on Keras.io. The link is on this slide. Thanks for watching.